In this video, we are going to go over credit risk in a loan portfolio and concentration risk. Let's start with some simple models of loan concentration. Some of the things we're going to talk about is migration analysis, which tracks the credit rating of firms in a particular sector or ratings class for unusual declines. On the next slide, we'll get more in detail on that, but it's pretty much when the credit rating changes or the risk of the credit rating changing. The loan migration matrix reflects historic credit rating experience of a pool of loans and serves as measure of the probability of the loan being upgraded, downgraded, or defaulting over some specified period. It's pretty much the probability, the odds, the chances, the risk of something moving within their risk level, changing risk profiles. Widely applied to commercial loans, credit card portfolios, and consumer loans. Let's take a look at it at the table. So this is a simpler table on what they're doing here. And let's talk about this here, for example. Let's say you have a pool of loans or bonds or whatever, there's a rating of between A and AAA. So you got A, AA, AAA. So they're saying that when you start the period, that's where you are. Now, what is the probability of ending the year in the same range? 0.85. However, keep in mind that you can still shift in a negative way if you're AAA and move down to AA or to a single A. Sure, you're still in the same pool, but you did get downgraded. So what I'm trying to say is that this table could be expanded to account for each one of the levels, but the idea, the concept is the same. The probability of something that is A, between A and AAA, to go down to triple B or double B or B, 0.10, about 10% chances of that happening. Another way to look at it, sometimes that 10% of those will go down. So it's just a historical, it just depends how you want to interpret or measure or discuss the item. Going from A all the way on to Z, to one of the C ones, you're looking at 0.04 or 4%. And if going all the way to a D, there's about 1% chance. So it's very unlikely, but it still could happen. Now, the same way I mentioned that AAA to AA to A could be a downgrade. It's just that not as bad as going all the way to B. Also consider that if you're single A, just a single A, 1A in your rating, going down to triple B, because that's just one step, it's more likely than going from triple A to, let's say, to the single B. It could happen, but it's less likely. So these could be broken down in some more, but generally speaking, that's the idea. And the rest is read the same. From triple B going up is about 12% chance, but triple B and B going down is about 3% chance, and about 0.83 or 83% of staying within the same range. Notice that they all add up to 1. This is probability. It's called exhaustive. 85 plus 10, 95, 99, 100. Same thing here. They all have to add up to 1 because probability goes from 0% to 100%. So more on the simple models of loan concentration. Management sets external limit on maximum amount of loans to be made to individual borrower, sector, or geographic area. These are the concentration limits. So let's say you're a bank and you're willing and you have about $100 million that you can lend out. Let's talk about individual borrower. You wouldn't lend the entire 100 million to one borrower. That's a very high risk situation. So you can put a limit on how much money you will lend to an individual borrower. Now, it is true that in the real world, sometimes a big company or a big corporation, we want to borrow a lot of money and it exceeds that amount. What banks do is they join forces with other banks in order to facilitate the loan. That is quite common. A sector. Let's consider like an industry, for example. You don't want to put all your loans on one industry only, because if that industry has a downturn, then everybody in your loan portfolio just went up in risk. So you want to diversify your sectors and your industries as well. Geographical area, similar to the industry, while you may put a lot of loans in different companies and people in a specific city, you don't want to have all your loans in that city. And that puts your risk of, it could be a city, it could be a state, it could be a country. The boundaries just depends on how you're managing it. But the point is that this is about not putting all your eggs in one basket. And that's how you do it. The way you calculate that concentration limit, there's a thing called the maximum loss as a percentage of capital that you may incur with those loans. And then you multiply by 1 over the loss rate. Or you can just divide it by the loss rate. You get the same number. Here's an example. Management caps losses at 15% of financial institutions' capital to a particular sector. So they're just doing a sector, but this would apply to any of the other items we spoke about. You just get a percentage. That is the maximum they're willing to lose in that sector. And estimates that the amount lost per dollar of default loans in the sector is 40 cents. That's about 40%. So what you do is you take your 15%, you apply it to the formula that we just saw in the previous slide. You also see it here. So 37.5% is a concentration limit of loans for that particular sector. So whatever capital you have to lend out in your financial institution, only 37.5% should go to that sector, whichever one it is. As you can see, because of the way the formula works, the higher this 0.4 or this 40 cents, which means riskier, will bring this number down. Diversification and modern portfolio theory. Generally speaking, what we're saying is that the same way you can diversify a portfolio with stocks when you're in the investment side, you can do a similar practice with loans, risk versus return type of approach. This is an example of what the efficient frontier looks like. Notice this line here is where it's cutting off at that point. And let's start discussing a little bit of this to do a refresher on efficient frontier and portfolio theory. The reason the line is there is because you don't want to invest or have anything in this line below. And the reason is because if the y-axis is the returns and the standard deviation here's the risk, let's say you have one on this line, on this point on the line. Well, for that level of risk, you might as well be in this point of the line because you get more returns for that level of risk. So you never want to be in this line. Matter of fact, you never want to be below this line here. This line that starts at B, let's say it starts at B and moves this way. That's where you want to be, somewhere on that line. Anything below that line, whether it's in the white area or on this line down here, it's inefficient. All you have to do is move things around a little bit to change your portfolio to where it then falls anywhere in this line up here. To give A and B as an example, A has this level of return, whatever it is, let's say 10%. And let's say it has a 5% standard deviation. So 10% return, 5% standard deviation. Well, for the same 10%, you have option B for a much lower standard deviation, let's say 2%. So rationally thinking, you should take a 10% return for this level of risk instead of taking a 10% return, the same return for a much higher level of risk. Same would apply if we go up the line here. There was a point here, there's a point D. If you're going to be at this level of risk, you want to pick the one that is on the line up here because you're getting more return. So A is never a good choice, no matter what. Between B and C, that depends on risk tolerance and other items, but they're both as efficient. One has lower returns, but lower risk. This one has higher returns, but higher risk. These are your formulas for calculating expected returns and variance of a portfolio. Now, the expected return is a weighted average. The variance, which we'll use to get the standard deviation, there's many ways to calculate it. That's just one of them. I just want to point out a key element here. This is variance, sigma squared with a P, sigma squared with an I for each individual item. Do not confuse this with this, or this one with these down here. When you have sigma with one letter only, then what you have is standard deviation of each item. Here, when you have two letters there, that means the covariance between those two. Now, this is not the only way to calculate variance and eventually standard deviation of portfolio. There are other methods. Look at the examples in the textbook and how to calculate it. But if you find the other one, as long as you get the same result, the number, it's fine to have your preferred way on how to calculate standard deviation. We will pause this video here, and we'll have a part 2 coming up.